Hello, everybody. Welcome to our weekly reading group on Zoom. Everybody is welcome to join. You can find the details in the description down below. Today, Jesse will be sharing his paper, Consistency Trajectory Models, Learning Probability Flow ODE Trajectory of Diffusion.
All right, cool. So yeah, thanks for putting me into this sharing club, and I'm going to share our recent work, which is called the Consistency Trajectory Models, in short CTM. And I'm Jesse Lai from Sony AI, and Dongjun Kim is one of our the first authors. This work was done during his intern at Sony AI, and these are our collaborators, and it's a great appreciation to them. Okay, so I guess you are pretty familiar with diffusion models, but before I jump into the detail of CTM, let me briefly recap what a diffusion model is. So diffusion model, as you may know, is we starting from noise and then gradually use the network to learn how to gradually remove the noise. So going from noise, and we gradually remove the noise, and then we can get a new generated image. So this kind of process is governed by an ODE. And this ODE, in short, is called probability flow ODE, and it is expressed like this formulation. So when we are doing, sampling in practice, we use a neural network to approximate this function, which is the gradient log density, and people call it as a score function. And once we learn it, then we replace this score with the neural network parameterized stuff, and then we initialize with some noise and solve the ODE backward, then we can get a new image. So this fantastic stuff is introduced in Yang Song's paper, Score SD. And why this is important is we know diffusion model is very excellent in generating good samples, but it is very slow for generation. And we can know why it is slow from this ODE solving point of view. So perhaps you may know that solving ODE, we need to start from some initial condition. Here is a noise. And then we are going to gradually use the slope information to approximate the solution trajectory, and then move step by step to get to the plane. Right. So no matter what we do, no matter how small this time step, the movement is, we essentially will have the discretization errors when we solve this ODE. And as you can see, that we need to prepare a bunch of steps to do the generation. So it is very slow by design. And you may naively think, okay, why not just do, say, 2 long jumps? And naively, we may get some generation. However, when you use a large jump, then you will get much larger discretization errors. And this will get your sample much worse. So there is a natural trade-off between the sampling speed and the sample quality. All right. So a lot of works are trying to improve the diffusion models in terms of the sample qualities or different perspectives. So from our lab, we have one of the work which is called FP Diffusion. It's trying to improve the diffusion models on for better density estimation by imposing some mathematical structure, but I'm not going to dive into it. And in the same time, there are several works kind of done by other institutes say like this work is done by U of Texas, is trying to improve the diffusion model sample qualities. And what is quite well known is consistency model from OpenAI, which is uh, aiming to do one step or like few step generations with diffusion models. However, we found that these three concepts are essentially the same in terms of theory. And this is proof in this short paper by us. So the question now is like, can we empirically achieve all of the purpose, like a good density estimation, good sample quality, and do the sampling fast with a unified framework? So this is the question. And the answer is the CTM, I mean the consistency trajectory model, which is just freshly accepted at iClear this year. So, all right, this comes to our topic, consistency trajectory model. And actually, we just released the code, so you can check the webpage later. All right, before I dive into the CTM, is there any questions so far? All right. So for kind of like a TLDR, like a CTM is a diffusion-based method that achieves a SOTA generation with only one step. So here are some random samples generated by CTM. And more benefit of CTM that I'm going to talk about this later is like a CTM can not only generate high sample qualities with fast speed, one step, but it can also enjoy like a diversity generation plus stable training. I'm going to explain all of this later in detail. All right. So somehow you can trust like CTM is a good model if you are tracing with this kind of features. Okay. So let's talk about how, what's the training mechanism of CTM. So if you are somehow like know something about the consistency model from OpenAI, the idea is quite similar, but not much. Not exactly the same. So for CTM, we call this CTM network as a CTM model. In notation is G theta. And the first argument is starting points, and the second argument is starting time. The last one is ending time. All right. So for CTM, we can do the distillation. What I mean is like if we have a well-trained diffusion models, and what CTM is doing is like it distill the information from the teacher model so that it can do one-step generations. How we do that is first we random sample xt at random time t, and then we random decided what's the endpoint. In this notation, it is s. Okay, then we decide randomly at which interval we are going to distill the teacher information from. So this in this notation, it is from u to t. Okay, so what the CTM is doing is like first we use the teacher model to solve with ODE solver for random state from t to u. And from this interval, this is what we are going to distill teacher information from to the student model, which is CTM. How we do that is like the training target is bringing this green dot to this brown dot. On the other hand, we use CTM model to directly pull the xt, starting from xt till this endpoint, which give us the orange dot. So essentially, we are trying to match the prediction at this level. At any time s. But we found that in order to get more like a perceptually good samples, it is good to pull it back again to the very clean sample, which is at time 0, and get us the X target and the estimation. All right, so far so good. So in the high level idea, because SUT are random during training, so when SUT are random run through all of the like possible choice, we are going to learn the entire solution trajectory. Plus, like, yeah, we are going to learn the entire trajectory. Yep. Okay. And in order to make the information pass from the teacher model to the student model more easily.
Okay.
Okay, I guess I won't leave the meeting anymore.
All right, so shall I start?
Sure.
Okay, cool. So like yeah, I mean CTM can learn the entire trajectory because like the SUT are random. And like in order to get visual qualities, we do additional like push forward to the very clean, so that we can use whatever like LPIPs over here to get a better like perceptual quality of the generations. And in order to make the teacher information pass through to the student more explicitly, we use the stop grade over here. Right. So let me dive into this part more. Okay. Indeed, what CTM is quite surprising is like with some tricks, like say GAN, in short, we can achieve the student model, which is the distillation model, like outperform the teacher model, which is the pre-trained different models. So what I'm saying is like this. Here is the true solution trajectory decided by the ground truth solution. Ground truth probability flow ODE. So here is the true generation starting from some noise. And what we do to obtain the regression target is we pull the solver from the teacher and solve it from T to U, where U is random, and then push it to the step S, and then push it more to the 0, the very clean, to obtain this regression target X teacher. On the other hand, for the like student model, what we did is like, okay, we started from random XT and then push it to S, and then S directly to 0 to obtain here. All right. So like the CTM loss, as I mentioned, is trying to match in this gap, the teacher and the student. However, no matter how well the pre-trained model is, there is definitely have some errors between the true sample, the true score, and the teacher. So there is a gap between the ground truth data and the teacher regression target. All right. So how we get rid of this gap is the GAN loss. So here we impose a directly training signal from the true data. In GAN, the true is the data, and here the fake in the GAN training is this student genetic samples. So with this, we can mitigate out this error. The inherent errors from the teacher and the pre-trained from the pre-trained teacher model and the true teacher models. So that's the student, which is the CTM, can beat teacher. Okay, so here is the example. The left-hand side is the teacher model, which we choose it as the EDM and the right hand side is the student model, which is this CTN model. And for ETM, which is teacher, we use 79 time step for sampling, but for CTM we use 1 step. All right. I will have you to focus on this part. I mean, this is called a kimono it's kind of a traditional Japanese style of like costume. Like you can see that the CTN generations can have more fine-grained details. And this is thanks to the GAN. And actually with the GAN, you can clearly see that the CTN model outperform the teacher model. Okay, so far so good. Okay, so I explained how we do the CTM training and its mechanism that can achieve student outperform teachers. Now let me focus on how we do sampling. So CTM can support 1-step samplings plus like a few step sampling that I'm going to explain later after this. So for 1-step sampling, once we get like a well-trained CTM model, how we do 1-step is starting from random noise, and then choose the starting time to be 1 because 1 is the very noisy time step, and then thirdly output the end time to be 0. Then this will give us the 1-step generations. So here, this is the 1-step generation of CTM, and you can see that CTM actually contains more fine-grained details, as I just explained. And you can see
in the comments.
Yeah. Oh, okay.
Somebody's asking about the butterfly losing detail, I think 2 slides ago. And then somebody also is asking about the architectures of the teacher and student networks.
Oh, yeah. Why the butterfly is losing details in opposite first column. Okay. I guess you are talking about this. So for the butterfly, yes, perhaps the game cannot capture like which part to make the fine-grained detail better. But if you focus on the background, actually the CTM contains more like details compared to EDM. And this like the more accurate background can actually improve the FID quite a lot. So yeah, I mean, GAN doesn't know which part to make the detail better. But in general, like CTM, you can see the background has more details. And do teacher and student follow same architecture, or have you tested some smaller architecture for student? Oh yeah, so for CTM, we use the same architecture both for teacher and student, but it could be quite interesting to test different architectures, like smaller or cheaper architectures, yes. So, all right. Did I answer all of your questions, or?
Yeah, those are the ones I'm seeing right now. So I think we're good.
Okay. Okay, cool. Okay. Yeah, so yeah, we are talking about the 1-step generation, and here are more samples, but you can check it in detail later on the project page. And yeah, I mean, like here is just some numerical values. Like this is the FID score, and you can see like CTM is like even better, like 1.98. It's even better than the EDM, which is 2.01. And like over here, if you just focus on 1-step generation, 1.92 is even better than where's EDM. Oh, okay, yeah, here, 2.44. And what is interesting is like, because the natural question is like, oh, I saw the question. Oh, yes. So like for CTM, in terms of the training stability, the CTM loss has 3 losses function. One is the CTM. Let me. go back to here. One is the CTM loss over here. And the other one is the score matching loss, which is you choose S to be T. And this will give us the infinitesimal jump. And infinitesimal jump is exactly the same as this score function. So CTM can directly use the DSM loss to help with the training. And the other one is the gain loss over here. So what is the significant factor is at the initial stage, we use CTM plus DSM to make the learning stabilize, and the gain loss can improve the qualities a lot. I mean, even achieve the student beat teacher. So in order to achieve student beat teacher, gain loss is quite important. Otherwise, the student model will always be bounded by the teacher performance. And we have a complete. Yep.
What are the benefits of compared to just training consistency models with gain loss?
Yeah, so we actually also have that as an application study. The gain training can improve CM performance, but the performance is not so, I mean, not at the level of CM, like here. This is the, oh no. Oh yeah, here. The CD plus gain.
I guess you used the previous paper's results. So I'm wondering what will happen if we use this exact same architecture and training configuration.
Oh yeah, this is the same configuration. Like
Oh.
before CM didn't have the gain training, and we use the same configuration, train it exactly the same as CM, but the output is different, and this is the result.
Okay, so can you explain like what would be the reason why CTM plus GAN outperforms CD plus GAN? Because like if we use only one step, then their solution should be same, right? So
yeah, so actually this is quite a good question. So for CM, if you remember, like they always do the local consistency, which is solving from t to t minus 1. And okay, so they solve from t to t minus 1 and then use the student model to bring it back to 0. And also starting from t to 0. This is the CM training. This is extremely unstable. This local consistency is not so stable for the training. But for CTM, we use what we call the soft consistency in our paper, which is like we randomly sample U between S and T. And this U is like random. I mean, it can like freely decide what teacher information will be distilled from. So with this random U, we can stabilize the trainings. Plus, we can have teacher information, teacher signal training pass through to the student more directly compared to the T to T minus 1. So this is one reason the consistency loss are different. The second reason is for CTM, because when S is exactly the T, this gives us slope, the infinitesimal slope. And as an initialization of CM or CTM, we initialize it to the same way that the pre-trained diffusion models, right? So for CTM, because S is close to T, then this is exactly the slope. So we are actually gradually starting from the initial information from the slope gradually to the like this kind of long jump. So this can stabilize the training and also get better performance. So the reasons are twofold. One is the soft matching in our CTM mechanism. And the second one is for CTM, we can naturally incorporate the DSM loss, I mean, denoising score matching loss in the training pipeline. So hope this answer to your question.
Okay, thank you so much.
Yeah, thanks. Yeah, so yeah, actually I skipped a lot of details in the training mechanism explanation, but yeah, I mean, what I just explained is pretty much what I want to say. Okay, so like 3 things over here. Like CTN can outperform the teacher, and like it can also outperform the consistent model plus GAN. And what is surprising is like whether, because in CTM we incorporate the adversarial training. So the question is like whether the CTM will be dominated by the GAN. And the answer is no. Because if you compare the like the likelihood is actually at the low at the SOTA level, so it doesn't suffer from the mount collapse compared to the GAN training.
Sorry, I have a question.
Yep.
Can you comment on the U, the first U that you choose, like in terms of signal to noise ratio? So how much noise is in the data for the first U that you choose in your setup?
Do you mean this U?
Yeah. So yeah.
Yeah, so yeah, they are in the training, the T is randomly chosen. I mean, everything is random once U is lying between S and T.
Okay, so the U can be also very close to the capital T in training.
Yeah, it's totally random.
Okay, thank you.
Yeah. Yeah, so yeah, this is about one-step generations. And for CTM, we can also do multi-steps. So let me explain a little bit what I mean the baseline. I mean the baseline means the consistent model do for their multi-step. Okay, so for their multi-step, the capital T is the very noisy manifold, and 0 is the very clean manifold. How they do multi-step is they do one long jump from very noisy to clean, because they can only do like a noisy to clean jump. And once they achieve the clean, they add noise back to the less noisy manifold T1, and then bring the sample back to 0, I mean very clean one, and then do this backward and forward. So this is called this is what they call the multi-step sampling for CM. In CTM, because we know the entire solution trajectory information, so we can gradually move from the very noisy and then little by little to the very clean. Okay. So if we think it in this way, like the CM or the baseline multi-step sampling, it is totally stochastic. But for CTM, we can have some deterministic sampling like methods. Okay. And what the issue for the CM's multi-step sampling is like, if you go from very noisy to clean and add noise back and then noisy to clean, there are some overlapping regions, and this will give you accumulation errors. And actually, we proved it that for the multi-step sampling in CM model, they will gain, in the worst case, they will get a lot of accumulation errors. But for CTM, we don't have this kind of overlapping intervals, so that we can avoid the accumulation errors. All right. Yep.
My question is, like in EDM paper, the author mentions that adding noise sort of eliminates the approximation error made by a neural network. So they should sometimes stochastic sampler are better than deterministic sampler. So
Yeah,
How do you
I
connect? Yeah.
yeah, I can add something on top of this later, but yeah, I mean here I introduced the multi-step sampling of CN, and in contrast it is like deterministic sampling from the CTM. But indeed we have a unified sampling scheme which is called the gamma sampling. Like CTM can do this way and this way, and you can choose whether you add noise or not. So yeah, I can explain more later.
Okay, thank you.
Yeah, thanks. All right, so as I explained over here, like CM models, like their multi-step sampling may have the accumulation errors like over here, and this is evidence over here. Okay, so the blue line is CTM, and the x-axis is the sampling steps, I mean NFEs. The quality is in the y-axis, so I mean lower is better in terms of FID. You can see that for CTN, if we increase the sampling steps, we can consistently get better quality, which means you can trade the sample speed for quality. However, for CM, you can see that if we increase the sampling steps, I mean the quality just like get worse. So we hypothesize that this phenomena is due to the accumulation of the CM multi-step sampling. On the other hand, because CTM can afford like a long jump, which is how we do this kind of sample blue line. On the other hand, CTM can also do infinitesimal jump, which can give us the slope or the score. And if CTM model plays as a score, we can plug it into any solver. For example, the Hun solver, like the EDM. And you can see that with CTM model placed as a score, by using Hun solver, we can get like similar performance as what we got from the like EDN, which is show over here. Okay.
Does this tendency also hold when you combine with gain loss? So
Oh yes, yes.
yeah. So as far as I remember, your FID on C510 is like 1.9. So like in that case, if you use like 5 steps, can it be lower than
So
216?
here it is not combining the gain loss because we want to see how the CTN training, I mean, how the CTN training objective affects the speed and quality. So here doesn't contain the gain.
Okay, so even if we use GAN, we still see the similar trade-off.
Sorry.
Graph.
So for if we add in gain, the performance is roughly staying at the same level, which is 1 point something for Cypher. So yeah.
Thank you so much.
Yeah. Okay, so yeah, I mean CTN can give us a clear trade-off between the sample quality and speed. And at the same time, because CTM can know the infinitesimal jump, so it can also plays a role as score function. So we can use whatever well-developed differential model inference technique for CTM. Okay. And this is what I just mentioned. I mean, a summary of the flexibility of sampling. Long jump can provide us like a fast sampling, and infinitesimal jump can provide us the score information so that we can use off-the-shelf different model inference techniques to do inference. All right. Now let's talk about the multi-step, I mean details multi-step sampling of CTM compared to CM. So I explained to you that the CM the multi-step sampling of CM is long jump denoise and noise, denoise and noise, and it will get a lot of accumulation errors. On the other hand, for CTM, it is gradually denoising, so it doesn't have the accumulation error. Plus, it is fully deterministic. Indeed, for CTM, we can support more flexible sampling technique, which contains the CM's multi-sampling. So the idea is pretty similar to the extreme case like a CM, where we start from very noisy. And because CTM can know the entire solution trajectory information, so we can denoise it to cleaner manifold than T1. And then similar to CM, we add noise back to T1 level and then denoise it to much cleaner manifold compared to T2 and then denoise it. So following this process, we can have a freedom choice of gamma to decide how many randomness we need to throw in the sampling during the sampling. So at the extreme case, you can see that when gamma is 0, then it contains the CM's multi-step sampling. However, when gamma is 1, it is the CTM's unique fully deterministic sampling. And CTM's models can support any gamma from containing 1 and 0 and any numbers between it, which means CTM can do the multi-step sampling as CM or do the deterministic sampling. But for the CM model, it can only do this kind of fully stochastic sampling scheme. So far, so good?
I have one more question in this. I'm not able to understand the notation of time here. So you have capital T and then you have T1 and then T2 and then T0. So first you directly go, so where gamma is 1, you directly go to T0 from capital T and you come back to T1.
Yes. So yeah, let me explain it again. Sorry about the messy notations here. So for CTM, it can support gamma sampling where gamma is a pre-designed hyperparameter. When gamma is 1, it goes back to the CM's multi-step sampling. On the other hand, when gamma is 0, it is a fully deterministic sampling scheme. And you can also choose gamma in the middle, depends on your application. Does that make sense?
Yes, that makes sense. It's just that when gamma is 0, you go from T to T1, and then from T1 you go to T2, which is a noisier version.
So the capital T the upper T means noisier, and the lower T means cleaner.
So T2 is noisier or less noisier?
Less noisier, cleaner.
Okay.
Yeah. So
Okay.
we gradually move from the noisy T and then denoise it to the very clean if you want to do the multi-steps.
Thank you.
Yeah, thanks. Okay, so depends on your needs. You can choose gamma at your preference. So at one extreme for CTM, we can preserve the semantic meaning. So like you can see, when we increase the sampling steps, the cat generations remaining the same. On the other hand, you can choose gamma 1 in CTM so that you can see that the semantic meaning is totally changed. And if you want to do, say, like downstream tests, like in painting, you can choose gamma to find some sweet spot in the middle so that you can somehow preserve the semantic meaning and still get good sample qualities. And this is the unique features of CTM. You can choose the gamma freely. Okay, so just to wrap up, like a CTM model is a unified framework of the score-based diffusion model plus the distillation models. Because for score-based model, CTM can know the infinitesimal jump, which is the score. On the other hand, CTM can know the long jump, which is what the distillation model does. In terms of the training, there's a point I didn't mention, which is CTM can also do training from scratch. Even though I was focused on distillation, but CTM can also do it from scratch. And due to the soft matching of CTM, it can converge much faster compared to CM, and it is much more stable. And with the help of denoising score matching loss plus the gain, you can bootstrap your performance and even achieve student beats teacher, which is quite a unique feature in the distillation model. In terms of sampling, because the CTM knows the entire solution trajectory, so which means at one extreme is the slope. So you can use whatever well-developed inference technique in different models community. And we can have a clear trade-off between the sampling quality and the speeds, like the curve I show you. And what is surprising is like student can beat teacher with the help of GAN. And like a CTM has a unique sampler, which is called a gamma sampling. With gamma, you can control the stochastic to throw in during sampling, and you can control you can have more controllable generation. All right. So I guess this is the end of my sharing. So if you have any question, just let me know.
I'm just wondering what would be the next step from this. Yeah.
Sorry, what do you mean?
Your future plan.
Future plan. Yeah, I think you may know the what's that? The latent consistency model, right? Which is distilled from the stable diffusion and do one step. In theory, we can directly apply the CTM training pipeline. I mean, replace this LCM with CTM. And that could be one of our next plan. But yeah, I mean, yeah, as you know, it needs a lot of engineering work. So yeah.
Thank you.
And there are more things to explore actually. So yeah.
Thanks so much, Jesse. I actually have one question. And maybe this question doesn't exactly make sense because there's like some result that if I that wasn't shown, but which would clarify this. But like, to what degree does your method rely on like kind of the underlying flow you're trying to learn being something that being like sort of the probability flow of a diffusion model rather than like, I don't know, if you were to train, for example, some flow from t equals 0 to t equals 1 with some kind of like flow matching or something like that. Could you like, could you come up with some, could you construct an analogous kind of like consistency trajectory approach to just learning like the trajectories of this like arbitrary flow that you've learned? Or is it like, is there some result here that depends on it being like Markovian?
Yeah, I guess I get your question. So in principle, I mean, in principle, the whatever flow matching or diffusion model does is like what these two methods do is like here is the data distribution and here is the noisy distribution. We're trying to do sort of interpolation but we need to make sure that the intermediate densities follows the the so-called focal plane equation. So no matter how you design the flow, either following the probability flow ODE or the straight line like the flow matching, once you follow that focal plane equation, that's you can do whatever distillation.
I see. Okay.
But for the flow matching, I think their distillation is much easier because like essentially the line is straight line. So you somehow don't need this kind of complicated way to distill. This is my intuition. So yeah.
Can you elaborate further why we need to know the focal plane? You
Yeah.
use
So essentially like essentially we need to keep the density evolution to satisfy the focal plane equation. I mean, no matter what the flow matching or the different model is, like in theory, it should satisfy that equation by design. So, sorry, let me rephrase it. Okay, so in order to interpolate these two, there is a focal plane equation, and how you interpolating, there are actually many ways to do that. But no matter what, once you fix the two endpoints, you need to follow the focal plane. So what the rest is like how you design the interpolation, like trajectory. So it's more like from the theoretical point of view. Yeah.
What was the compute that you required to perform the experiment?
Could you please repeat that again?
I'm asking about the compute that you required to perform the experiments.
Okay. Yeah, so for ImageNet 64 by 64, we were using 800. Oh, sorry, my cat is walking around my PC. Anyway, so we are using 800 compared to CM. They need 64 800s, right? So it is quite cheaper. And in CM, it actually converges much faster.
Oh, nice.
Yeah.
but I guess in your method, I think you have to simulate the ODE to perform the global matching. So yeah.
The soft matching, you mean?
Yeah, so you solve the
Oh.
ODE from T to U, and how much cost does it bring?
Yeah, so because it is random, so there is no like a certain amount of time how many, I mean, at what expense you need to solve from T to random U. But in general, we found that the runtime, the total runtime, DTM converge much faster. So if you compare the runtime per iteration, then CTN may be expensive, more expensive compared to CN because it needs to call the solvers, like random solver for many random steps. But in terms of the total training runtime, CTM converge much faster.
Okay, thank you.
Thank you.
And my another question is like if we fix the U to 0 and T to capital T, then we just reduce to the previous distillation method, like yeah, where they just generate the bunch of pairs and then just try to predict the solution, right?
Yes.
If we do that, and if we are only interested in one-step generation, then should we expect the same level of performance?
Yes. Yes. But in that way, for ImageNet, the training will be much expensive, much more expensive, because you need to solve. I forgot perhaps 79 for ImageNet 64 steps.
Okay, thank you so
Yeah.
much.
So yeah, just add on a little bit, like our self matching is for it is more like you can also balance between the training stability plus the training runtime. Like if you just use the local matching, the training is quite unstable, but it can the runtime is faster per iteration, but the total runtime is not like faster compared to CM because their instability. On the other hand, if you use the solver to solve it all the way, then the training could be very stable because it's just essentially the autoencoder. But you need to sacrifice your runtime a lot during this kind of ODE solving.